So recording has hopefully begun. Yep, there we go. Okay, so I hope you can all see my screen okay. And
perfectly.
Hopefully you can see it even better now. Okay, so we last time talked about general concepts of selectivity and regioselectivity in relation to aromatic chemistry, primarily. But today we're going to really get into more generally oxidations, reductions, and carbon-carbon bond formation, hopefully. So we're going to start out with a pretty fundamental problem in alcohol oxidation. Now, let's start with a primary alcohol here. And then we do an oxidation using, let's say, something like the Jones oxidation. So chromium 6 in sulfuric acid, acetone, water. Well, initially you get the aldehyde, but in the presence of water, it forms the hydrate. Most aldehydes will form about a 50% hydrate. Some aldehydes can be a lot more. Of course, this depends on the solvent, etc. But in aqueous solution or a solution with a lot of water present, hydrate formation is very common, which gives our hydrate here, which is sometimes referred to as a 1,1 diol. And then a second oxidation gives us the carboxylic acid. Now, the really important part of this mechanism that I really want you to take home is that the second oxygen atom does not come from the oxidant. And if you ask most undergrads and even some grad students where the second oxygen in a carboxylic acid comes from, a lot of people will say the oxidant, and it is entirely wrong. There are some cases where it's true, but certainly all the most common oxidations, it is not the case. And this is something that makes me really happy, to be honest, because a mechanistic understanding of this reaction, this oxidation of a primary alcohol, does actually lend us enough insight to then predict reagents to do this transformation. So very simply, I could ask you, well, based on the mechanism that I've just shown you, how would you only get the aldehyde? And aldehyde is very useful, so we often only want to get the aldehyde. And I would like to believe that with that mechanism that I've shown, you can realize that, of course, if there's no water, then there will be no over-oxidation to the carboxylic acid. So finding ways to do that would be great. Anyway, so chromium trioxide, of which sodium dichromate is a precursor or a standard reagent to be used. Chromium trioxide can react with alcohol, secondary alcohols to make ketones. Again, this is nothing new. You know, we can draw that going like this, plus and minus H plus for the transfer, and then we can lose the chromium in an oxidation step. So if we're in water or something, then some kind of nucleophile or base can remove that H. That then gives the ketone shown here, and chromium 4. Now, chromium 4 is actually not very stable, and so what you get happening is a disproportionation reaction, whereby 2 times chromium 4 gives chromium 3 and chromium 5. And chromium 5 can oxidize another alcohol to give chromium 3. So whenever you are doing a chromium-based oxidation, you often end up with a kind of green sludge at the end, and green is the color of chromium 3 in aqueous solution, whereas chromium trioxide is orange, especially sodium dichromate. Okay, so like we said, that's a ketone. Obviously, you can't really over-oxidize that. But based on the mechanism that we had at the start, well, if we have a organic soluble chromium 6 source, which a classic example is pyridinium dichromate, then that will work in dry DCM to oxidize an alcohol to an aldehyde. Okay, there are other equivalents. You can use pyridinium chlorochromate rather than pyridinium dichromate, but it's the simplest way to oxidize from a primary alcohol to an aldehyde. Okay, just remove the water, remove the second oxygen. Okay, so that works well enough to some extent, but it can be a bit problematic at times, and it does generate a large amount of chromium waste. It can just be a bit of a mess. So a lot of other methods are used that are often a lot milder as well. So the first, and honestly one of the most commonly used, is the Swern oxidation. Okay, the Swern oxidation is a modification of a reaction called the Moffat oxidation. And very simply, all of these methods might be considered activated DMSO methods. Okay, so with the Moffat oxidation, it is DMSO plus DCC. Okay, but there are a lot of different options. The Swern, however, is the most common, most reliable, and typically most liked. Okay, so how does this work? Well, first we start with DMSO. Now, I'd really like to draw your attention to how DMSO has been drawn here. This is a much better way to draw DMSO compared to this one. Okay, first of all, there's no such thing as a sulfur-oxygen double bond in DMSO. It just doesn't happen. If you like, the second bond is an ionic bond, is some way to think about it. It's certainly quicker and easier to draw it like this, but it is a less accurate representation of the structure. So as much as possible, I'm going to try and remember to draw it as the S plus O minus version. One of the reasons that I really like this is it really does guide you towards the reactivity of this molecule. Okay, we really do know that it's got an O minus, there's a large buildup of negative charge on that oxygen, and with most of our mechanisms, we often start from the atom with the negative charge. So let's do it. We attack oxalyl chloride, okay, which is a very reactive reagent. So we attack the carbonyl, which breaks the bond. The bond then comes back down to kick out chloride. Okay, and the important thing is that we do this at minus 78 degrees Celsius. Okay, so the chloride then can attack the sulfur in an SN2-like fashion, which kicks out carbon dioxide, carbon monoxide, and one equivalent of chloride. Okay, so what that ends up looking like is SCl plus with a chloride counterion. Okay, and that is a dimethyl chlorosulfonium ion. Okay, so the chlorosulfonium cation is the real oxidant. The only thing to remember is that chlorosulfonium is unstable over minus 40 degrees C. Okay, now at greater than minus 40 degrees C, what happens is that the chloride minus can attack the chloride of the chlorosulfonium to give chlorine gas and dimethyl sulfide. Okay, this obviously isn't great because that's the end of your reaction and you've just generated chlorine gas through quite an expensive fashion, really. Now, what's interesting is that if you actually take dimethyl sulfide and react it with chlorine at minus 78, then that is a way that you could actually generate the same intermediate, arguably using a lot cheaper reagents, just dimethyl sulfide and chlorine gas. And under those circumstances, it's called, oh, wrong way, it is the Corey-Kim oxidation. And this is often actually very good on industrial scales because you're not using large amounts of oxalyl chloride and you're not generating large amounts of carbon dioxide and carbon monoxide. So that is a good way to scale up this process if you don't want to produce lots of carbon monoxide. But you need a chlorine cylinder. Okay, so now we've made our chlorosulfonium ion, what do we do with it? Well, we take lone pair of the oxygen, which attacks the sulfur, kicks out our chloride, and we lose HCl gas. So there's a lot of gas being produced in this reaction. Okay, one equivalent of carbon dioxide, one equivalent of carbon monoxide, and then HCl gas as well. So that then gives us a compound as shown here, an alkoxy. Oh, goodness me. I said I would apologize for my handwriting a lot, and now I am again. Sorry about the handwriting. So we've got an alkoxy sulfonium cation. And it's important that you have to premix your DMSO and your oxalyl chloride at minus 78, and then you add your alcohol still at minus 78 before you allow it to warm up at all, though often you keep this at minus 78. And then you treat it with triethylamine. It's very important that triethylamine is done as a second step, or possibly even a third step if you want to consider the addition of alcohol. So, So this is step 1. Step 2 is activation of the alcohol. And then, oh goodness, why won't this go away? There we go. 3 is triethylamine, which is breakdown. Okay, so triethylamine is a base and it has 2 possible protons that it could deprotonate. This one here, which would give you the oxidation, and this one here. Now, the most acidic one is going to be the one that's closest to the cation here. Okay, so our lone pair on the triethylamine deprotonates this H and generates an anion next to the sulfur. Okay, and this then is a sulfur ylide. Okay, a lot of you might recognize the term ylide from phosphorus chemistry. An ylide is a compound where you have a negative charge and a positive charge on 2 neighboring atoms. The name comes from something I'll talk about in a minute. Let's just finish the reaction. So we generate our ylide, and then that ends up deprotonating in this mechanism here. Yes, it's pericyclic. The reaction goes in a circle. We won't talk about that for now. And that gives us our aldehyde. Okay, so the great thing about activated DMSO methods, such as the SWERN, they are effective for primary and secondary alcohols, and the amine base is necessary to break down the alkoxysulfonium salt. Okay, it's great for oxidizing primary alcohols to aldehydes, but even better, it's great at oxidizing multiple alcohols at the same time. Okay, so the ylide, for example, let's think about a cation. I'll just mention this briefly. So if you had methyl plus, then that is the methyl cation. If you had methyl minus, it would be the methide. Think of the IDE suffix, similar to chloride. So we've got the YL of the cation and the ID of the anion, which gives an ylide. Okay. Next, so here's a complex example that we will be talking more about later. So, very important thing. Never reveal an aldehyde in the presence of reactive functional groups. Okay? This is a brilliant strategy that's being used in this natural product synthesis that we will be discussing more later. So, if we use our SWERN reaction, then we use 2 equivalents of DMSO, 2 equivalents of oxalyl chloride, and we generate the bis alkoxysulfonium salt here. Then you add the triethylamine and you undergo a bis oxidation at the same time. Okay, so we get the desired dialdehyde. If you were to use another method, such as chromium trioxide, or the best method, in actual fact, for doing this reaction, because sometimes you want to do this, is actually ruthenium 404 minus, which is referred to as per-ruthenate. Ruthenate for ruthenium, and per because you've got a lot of oxygen there. Okay, that's ruthenium 7. Tetrapropyl ammonium perruthenate is sometimes referred to as TPAP, or the Ley oxidation. And I mentioned that because Steve Lay was my PhD boss. Anyway, what happens with chromium trioxide or perruthenate is that you oxidize one primary alcohol first to the aldehyde, and in this case shown at the bottom, you can see that the second alcohol is 6 atoms away from the aldehyde. So it cyclizes to form a hemiacetal. And that happens very, very fast. It's an intramolecular reaction. So we get the hemiacetal, which then acts like the hydrate that we discussed previously. And when that oxidizes, you get a lactone. Okay, that can be very useful sometimes, but here it is not doing what we want it to. Okay, so the Swern oxidation is actually a really brilliant way to ensure that you get the dialdehyde that you want instead of a lactone. If you want a lactone, then TPAP is the best reagent to go for. And I'm not just saying that because Steve told me it was. Okay, maybe I am. Okay, so functional groups have different kinds of reactivity. Reductions. We said at the very start that different types of functional groups, such as ketones and alkenes, can be reacted very readily to give different products. But for chemo and regioselective reductions, there's more of a question when you're looking at other substrates. So let's look at 3 different sets of conditions here. First of all, if we have this compound here, well, we've got a ketone that's conjugated and we have an ester. Now, if you have borohydride, I think we discussed this earlier, then borohydride, NaBH4, can go conjugate or it can go direct. Okay, it's a bit of a problem. If you add cerium trichloride, however, it actually goes selectively to only give 1,2 addition. 1,2 addition. Okay, and the incorporation of cerium trichloride into this system is known as the Luche, L-U-C-H-E, or Luche, if you're going to be very German about it, reduction. Now, the alternative, instead of using sodium borohydride, is to go for lithium aluminium hydride. The problem with lithium aluminium hydride is that it kills everything. It is very reactive. So it reduces both the alcohol, the ketone to the alcohol, but also the ester to the alcohol. So that can be useful, but it might not be what you want. And so the Luche reduction gives you the ability to be more selective. Now, what about if you want to reduce the ester in the presence of the ketone? That's a bit more problematic. Okay, esters are inherently less reactive than ketones. But what you can do instead is first hydrolyze the ester using sodium hydroxide, and then you can react the carboxylic acid with borane. Okay, borane is a selective reagent for the reduction of carboxylic acids. So borane, BH3, reduces carboxylic acids at best. It'll reduce other things as well if you give it enough time, but it's best for carboxylic acids. Now, the last one that we might want to think about is how do you reduce the alkene and not reduce the ketone? Well, very simply, of course, we can use palladium on carbon, but we do actually have an alternative reagent as well. Oop, wrong arrow. Arrow is down here. In order to get through to this compound. Oop. Oop, one too many. My apologies. And in order to do that, we can use Stryker's reagent. And that is this. Okay, Stryker's reagent is a hexamer, though it reacts as a monomer, of triphenylphosphine copper hydride. And you can probably imagine that the copper, we said before, copper is good at giving conjugate addition. Well, it does a conjugate addition of hydride. Here. Okay. So here is a useful table. Okay. This is a table of, how the various different hydride reducing reagents react. Stryker's reagent isn't on there because it's a bit more unusual. But good to know if you're in Canada because Stryker is Canadian. Anyway, so the weakest reducing agent in this list is sodium cyanoborohydride. And similarly weak is sodium acetoxyborohydride. That is also a very weak reducing agent, and that will also reduce imines. It will not reduce aldehydes or ketones under normal conditions. So if you want to selectively reduce an imine, remember that was useful for reductive amination, then sodium cyanoborohydride is a good one. Sodium borohydride is good at reducing aldehydes and ketones. It's not good at doing esters, amides, etc., etc. Lithium borohydride, though, can reduce an ester as well as the aldehydes and ketones. Okay, but it can't really touch amides or carboxylic acids. In order to reduce those, you need lithium aluminium hydride, or to completely reverse the reactivity, you can use borane to reduce the carboxylic acid to the primary alcohol. Okay, now in order to get a reduction from esters, amides, or acids to the aldehyde, it's a lot harder, to be honest. Esters, you can sometimes use dibal, which is a great reagent, though it's usually better at reducing down to the primary alcohol. And because the Swern reagent is so reliable, most commonly in total synthesis, you'll see a double reduction followed by an oxidation instead of a single careful reduction. An amide, if you do the lethal reaction on an amide, but keep it at very low temperature, like -78, then you can get the aldehyde. Again, not always reliable. And the carboxylic acid can be reduced to the aldehyde if you turn it into an acid chloride first and are very, very careful. Again, it's not really that reliable because the aldehyde itself is so reactive. Often the best thing to do is just reduce to the primary alcohol and then reoxidize. Okay, so I briefly mentioned dibal, and now I'm going to mention it slightly longer. The key thing I really want you to remember, though, is that dibal, or dibal H, or diber sometimes, DIBAH, sometimes it's called to. But dibal works better on paper than in reality. Okay. So, dibal, key thing here is it becomes a good reducing agent after reacting with a nucleophile. So if you're trying to reduce a ester, for example, the first step in the reaction is not attack of the hydride, but in actual fact, attack of the ester onto the aluminium. That generates a zwitterion. In actual fact, it's an ylide, which can then deliver the hydride intramolecularly. So, dibal reduces the most nucleophilic CO first. So if you've got the choice between, let's say, a ketone and an ester, because of the first step being the complexation, it will usually go for an ester first. The problem is it will go first, but not in 100% selectivity. And, you know, the better the selectivity, the happier we are. So we get the hydride delivery to give a tetrahedral intermediate. And this is semi-stable at low temperature. Okay. The reason for this stability is that the lone pair of this oxygen coordinates to the aluminium, and you have some stability here. Okay. This hemiacetal is not electrophilic, so it's only upon quenching with acid and water that you get a proper hemiacetal, which can then break down. That's the theory. It doesn't always work great because, unfortunately, sometimes the breakdown happens on its own anyway. Okay. So I will just mention dibal is best if there is an alpha alkoxy group on the ester. Okay, so something like that. Okay, because that gives you a more stable intermediate than is the case otherwise, because you get, instead of a four-membered ring forming, you get a five-membered ring forming instead, and a five-membered ring is more stable. So there's a more stable intermediate. Okay. Just going to redraw that slightly so it's not looking quite so ugly. There we go. So we have a more stable intermediate when there is this alpha alkoxy group. Okay. One case where you don't typically need that additional stabilization is when you're trying to reduce a lactone. Remember, a lactone is a cyclic ester. And of course, the reason is that the hemiacetal is more stable because it's cyclic. So cyclic hemiacetal is more stable than acyclic one. Okay, but you can still use this cyclic hemiacetal in various reactions. You just need to do something to make it open first. So if you use 2 equivalents of this reagent, then the first reagent actually acts like a base, which catalyzes the ring opening of the hemiacetal to give the aldehyde. And then the second equivalent does the Wittig reaction. Okay, so this works for dibal, but can we use something like this more generally? No. So if you take an ester, for example, and you react it with methyl magnesium bromide, you get a ketone. Okay, the acetal is not anywhere near stable enough, and it breaks down. Okay, and the problem is that an ester is less electrophilic, and a ketone is more electrophilic. And so if you add a Grignard reagent to an ester, you only get the diaddition product. Okay, double addition product only. Okay, and same thing happens with butyl lithium. Now, just note here for a second. Note the regioselectivity. It gives direct addition rather than conjugate addition. Okay, so let's say that we have a carboxylic acid or an ester or some similar derivative, but we want to make a ketone. How do we do it? Well, we could, for example, reduce the ester down to the aldehyde using dibal, maybe. We could take carboxylic acid, reduce it down with borane to a primary alcohol. Then we oxidize selectively up to the aldehyde. Then we could add our nucleophile, and then we could oxidize again. But you can see this is getting really lots of steps for really not very much transformation happening. So what's our possibility? Well, we can use amides as electrophiles. We actually saw this in the last lecture when we were talking about ortholithiation, and we said that we could generate an aldehyde by adding into DMF. So we have seen this. So you take your alkyl lithium species, it reacts, and you generate the alkoxyamine, and this is typically stable-ish under reaction conditions. Upon acidic workup, you get protonation of your alkoxide and protonation of your amine, and then you lose the dimethylamine to give your aldehyde. Great. However, this isn't perfect because the amide isn't the most stable electrophile. The aminal isn't the most stable intermediate. Okay, so a more stable intermediate would be better though. And Stephen Weinreb came up with a solution for this, okay? And this is referred to as a Weinreb amide for obvious reasons. So you start from an acid chloride and you substitute off the chloride. and you get this methoxyamide shown here called the Weinreb amide. Dr. Green loves this. He uses it a lot in his chemistry, but he's not the only one. It's a very good solution. So the thing with a Weinreb amide is that when you get attack from a nucleophile, you generate an intermediate, which is a 5-membered ring, a coordination complex. Of lithium plus or Mg2 plus if we're using a Grignard. This is a lot more stable. And the key thing here is that it is just a lot more reliable than using just a standard dimethylamide. And reliability, predictability is really what we're going for here. Again, upon treatment with acid, we get protonation and breakdown during workup to give us our desired ketone. Okay. And Weinreb amides are good for a lot of things. On the right here, I'm just showing, having pen trouble again. On the right here, I'm just showing good nucleophiles. Acceptable nucleophiles with Weinreb amides. So we've got the alkyl lithiums, we've got the Grignard reagents, we have various types of enolates. You can even use dibal. It's a very good dibal reduction here, or you can even use lithium aluminium hydride on this, which will give you the aldehyde. Okay, so both of these give aldehydes. Okay, so dibal and lithal, great reagents to use with a Weinreb amide to get an aldehyde. However, you got to think about whether it's worth it for your step count. Okay, so if you start with an ester, for example, in order to make a Weinreb amide from that, you need to hydrolyze the ester, turn it into an acid chloride, and then react it with the dimethyl hydroxylamine. Then you've got to add your nucleophile, the divalylethal. So you're looking at 4 steps. If you used dibal or lithal on its own and then a Swern reaction, 2 steps. So often that's a lot quicker, even though Weinreb is a very elegant solution to a lot of things. Okay, so here's some examples of the Weinreb in action. So here you can see you've got some relatively complex molecules here. Methyl magnesium bromide, it adds to the Weinreb ketone rather than the lactam, which is somewhat surprising. Could you expect the strain to promote the reactivity there? But no, the Weinreb amides really are quite reactive, which is really helpful. So you get your intermediate, and then that breaks down on workup to give the desired ketone. Like I was saying, you can do a dibal reduction to get the aldehyde, and sometimes this is the best thing to do because it's very gentle if you've got a very complicated molecule, as you can see here. And you can finally do a enolate addition to give this beta keto ester. Okay, this is pretty nifty. And one of the things that's really good here is that if you were trying to do this reaction, let's say with phenyl, benzoyl chloride, what would actually end up happening is that the oxygen would attack instead. Okay, so Weinreb amides can be even very useful with enolates. And I got a little bit ahead of myself there. Acylation of carbon. So, enolate reactions. So, this is a lovely reaction called the Claisen condensation. Same Claisen as did the Claisen rearrangement, but it's a very different reaction. So, let's look at this for a second. We take an ester, we react it with an enolate, and we get a ketone, which is more electrophilic. We said that earlier. Do we get further reaction or don't we? The question is, the answer is actually no, we do not. And the reason is because of the reactivity of our product. So let's consider a classic Claisen condensation, which is under thermodynamic control. So we take an ester and we use a relatively weak base. Okay, pKa of an ester. So the pKa of this proton here is approximately 25. The pKa of most alkoxides is between 16 to 18, depending on which one you're using. So we're using, by comparison, a relatively weak base. Anyway, we deprotonate and we generate our enolate. And our enolate can then react with itself, or with another equivalent of the ester, kicks out the alkoxide. So we actually regenerate our alkoxide. That, however, can act as a base or a nucleophile, but typically deprotonation happens a lot faster than a nucleophilic attack. So we actually get production of this conjugated enolate. It is stable and it is non-electrophilic. Okay. And this is the product under the reaction conditions. Okay, so in order to actually get the ketoester that we want, we need to then react it with H+. That then gives us our desired product. Okay. Now, the key thing here is that all of these steps are reversible, but the last one is not particularly reversible. Okay, so we can redraw this like this. Okay, this deprotonation is effectively irreversible. Note that the final deprotonation is reversible, but the equilibrium lies far to the right. And the reason for that is that we said that the pKa of our deprotonation, the pKa of our alkoxide at the start was 16 to 18, and the pKa of our ketoester is around 11. Okay, so K is approximately 10 to the power 5 to 10 to the power 7, which is a pretty convincing reaction to me. Okay, Claisen condensation, great reaction. It's such a great reaction that they gave it a different name when it's intramolecular. At which point it's called the Dieckmann condensation, and all the same arguments we made before are still the case. The only thing is we can, once we've made our enolate here, we can then react it as well as just protonate it. So what they've done here is they've reacted it with methyl iodide instead of acid. Now, the great thing about this, of course, is that it's under thermodynamic control and it can be really predictable. It's rare that thermodynamic control is this predictable, but when it works great. So let's consider this substrate here. Okay, we've got two possible sites for enolate formation and reaction, site 1 and site 2. Now, if you deprotonate at site 1 and then you react at our electrophile, which is our diethyl carbonate here, then you get this product. If you react at site 2, you get this product. The question is, which one do you get? Well, the one on the right can be deprotonated. Okay, so our ethoxide can deprotonate this, which gives this product. Okay, now this cannot be deprotonated to form a stable enolate. So this reaction does not happen, and this reaction does. Okay, now that final step being irreversible means that the equilibrium, even if you form some of this, will revert back to our product and keep going back to our starting material and then go to the product on the right. Okay, so this is an example of Le Chatelier's principle. So most commonly, in my experience, if you want a predictable thermodynamic product, you're probably going to be using Le Chatelier's principle to explain this. Okay. Next, more of this kinetic versus thermodynamic. Well, if you take the ketone shown here, well, you've got two possible enolate formations, 1 and 2, and we get reaction at the 2 position as the thermodynamic product. Why is that? Because there's 2 protons that can be deprotonated at both sites. So in theory, we can get a stable enolate in both cases. But there is a very important, very clever trick that's happening here. Okay, so we take our enolate. So let's just look at all of our possible enolate conditions. So if you deprotonate here at the 1 position, then you get the kinetic enolate. Okay, kinetic enolate is formed at the most acidic position under these conditions. Okay, so we deprotonate and then we react with our methyl cyanide. I think that's Mander's reagent. It's really good for these kinds of reactions. So we initially react to give the ketoester here. The problem is not that we're making cyanide. The problem is that when we do the second deprotonation, what ends up happening is that we end up with a very flat system. Okay, and the H and the carboxylate are now in the same plane and they clash, and they have to be in the same plane in order for there to actually be delocalization. So this enolate is destabilized by eclipsing steric clash with the aromatic CH bond. That disfavors planarity. And if the carboxylate, the methyl carboxylate, is not coplanar with the enolate, then it is not a stable enolate. It can't be. So therefore, it ends up actually reversing because this is not the most stable product. However, if we react on site 2, then we end up being able to do a deprotonation that is entirely favorable. Okay, so I'm just going to switch colors for that. Oh, go back one. This is favorable because there's no such eclipsing interactions here. And this is therefore a more stable enolate. Okay, so again, remember the final enolization is reversible, but it lies over to the right hand side because again, our pKa's say so. Okay. Let's look at another example of this. Well, stabilizing the intermediate precludes proton transfer under reaction conditions. So how can we get nope. Did something wrong here. My apologies. Okay, sorry, this reagent doesn't do it. Manda's reagent does completely the opposite. Oh, my apologies, my apologies. We got carried away. Okay. Okay. There we go. Better. Okay. Okay, now we have and there aren't a lot of Australian chemists of note, so I might as well just mention this one, Lou Manda. Anyway, Manda's reagent, however, does allow you to form the kinetic enolate product because essentially there is reduced reversibility. Remember, the key to getting a thermodynamic product is the reversibility of a reaction, if it's not reversible, it will not give a thermodynamic product. It can't. Okay, you've got to be able to equilibrate. So if we take our reaction and we use Mander's reagent, well, what ends up happening is that you get a semi-stable intermediate again. And there is a slow breakdown because now you're not breaking a carbon heteroatom bond, you're breaking a carbon-carbon bond. And so that makes this the rate determining step. Okay. So Mander's reagent, good for getting kinetic acylation. There we go. Next, more about carbon-carbon bond forming reactions. So we were talking about some single bonds previously. Now let's talk about some double bonds. And one of the best, most famous, blah, 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 reactions for making carbon-carbon double bonds is the Wittig reaction. He got the Nobel Prize in the 1970s. He actually shared the Nobel Prize with Herbert Brown, H.C. Brown, and H.C. Brown is responsible for a lot of the boron chemistry that people do these days, and Wittig did, of course, the Wittig reaction, but essentially they both got it for doing heteroatom chemistry. Wittig for carbon-phosphorus chemistry, and Brown got it for carbon-boron chemistry. So, things to know about the Wittig reaction. Hopefully most of you know this already, that an unstabilized ylide will give you a cis double bond, which is sometimes known as the Z double bond, and the stabilized ylides give you the trans, which is the E double bond. Oh, it says it here as well. And the thing to remember is that the Z reaction, Z selective reaction, the cis reaction, is under kinetic control. And the trans selective reaction is probably also under thermodynamic, is probably also under kinetic control, but it's a very different system. Now, the interesting thing about the Wittig reaction, like I say, he got the Nobel Prize in the 70s. He did a lot of the early work in the 40s and 50s even, and we're still not absolutely sure of the mechanism, which is really saying something. However, it seems that it is a 2+2 cycloaddition reaction that has a very weird shape to it. Okay. I'm not going into the Woodward-Hoffmann rules during this course. I would love to talk to you about it some other time. But for now, I'm just going to tell you that a 2+2 reaction, such as is drawn here, is symmetry allowed. But geometrically, unlikely. Okay, because what we're doing with these arrows, we're saying that this carbon atom is reacting with the top face of this carbon atom at the same time that this carbon atom is reacting with the bottom face of this one. So that's weird and unlikely. So what ends up happening instead is that the bottom component there has been redrawn by being flipped 90 degrees onto its side. Now it's interacting on the sides of the bottom component, okay, rather than directly above or directly below. So this is now possible, but still a bit weird, okay? And it is now, sorry? You had a question?
Is it going to be like a partial overlap, so it's not very favored because it's going with the opposite phase as well?
Well, I've not drawn in any phases here, and that's for a very good reason. Namely that in a cycloaddition, you've got both of them happening at the same time, which is, I know, a bit weird. I'm just going to draw this for a second, because this geometry that I've drawn on the side here, which is boxed in blue, this one is only possible with a large atom like phosphorus. Okay, it can't really work with something small like carbon. So just for 1 second, yes, I definitely want to keep those. I'm going to add in a new slide and we'll get back to it. So what's happening if you have 2 pi bonds? Okay. And I'm going to shade in, this is going to be the pi, and this one over here is going to be the pi star. So we've now got a second one doing this and this. Okay, so in order for these two to react with each other properly, the pi star is going to need to interact. And remember that what I showed you was them interacting on opposite sides. So I'm going to go purple now. So this interacted here, and this one interacted over here. Okay, and the same thing happened here and here. Now, the pi has 2 electrons in it. The pi star has no electrons in it. Okay, so the pi has to interact with an empty orbital. So this is going to be the pi star down here, and this is going to be the pi over here, because the pi star has to interact with a filled orbital because it itself is empty. So the interactions that I've drawn should show you that that's the case, because I now fill in these two, and you can see that the empty orbital here is filling with the empty one down here, and the filled one up here is interacting with the filled one over here. Conversely, on the left-hand one, I'll shade these two, and the symmetry is good. Both of these interactions, or these orbital interaction sets, are happening. Oh, nearly at the same time. Oh, can't spell. It's weird to think about it, but because you're looking at a filled interaction in a pi versus pi star, in a 2+2, you do actually have to consider them both, and they are both happening. This actually also happens with the Diels-Alder. Okay, so on the diene component, the HOMO is this one. Okay, and that interacts with the pi star. There we go. That interacts with the pi star of the dienophile like that. So we've got symmetry allowed. But at the same time, the LUMO of the diene, which looks like this, is reacting or interacting with the pi of the dienophile, not the pi star, but the pi. Again, both happen at the same time. I imagine that explained nothing and actually made things more complicated. Sorry about that. But yes, you're right to question it, but the thing is you've actually got a lot of orbital interactions happening at the same time, which adds complications.
Okay, yeah, no, I think I understand it. It's just how the phases are and where they're overlapping. I just never really considered it's going more diagonal. It was really hard to visualize. But I see it.
In the Wittig, it has to kind of go on this diagonal, but it can only do that with big fat atoms like phosphorus that are essentially have longer bonds. So when it twists, they can still interact. That kind of twist doesn't work with carbon. That's why you don't get a standard 2+2 with carbon. If you have some weird orbital effects, then it can happen, but it needs this weird kind of twisty thing going on. So it's got to be on its side for it to be allowed, and in order to actually work on its side, it needs to be phosphorus or something similarly large. Okay, so let's look at reactive ylid transition states. So I'm going to draw that as P plus, carbon minus. So when that interacts with an aldehyde, there are a whole bunch of things going on. Now, first of all, I am going to use a white pen to get rid of this phenyl. And I'm going to use a black pen to draw in the phenyl groups there. Okay, so because these phenyl groups are quite big, what ends up happening is that the R group here sits as far away from them as it can be. So it doesn't point towards the phosphorus, it points away. So the H points towards the phosphorus. Okay, pretty simple sterics going on there. Now, because the R group has to point away from all these phenyls to get away from it, then the methyl group, here, oh, what happened there? That was meant to be green. Okay, so the methyl group here is now on opposite side . So the R group goes away from the phenyls and the methyl group goes away from the R. Okay. What that means is that when you draw your intermediate from that, you get this initially. And when you redraw it, you get this. Okay, so the H's end up being on the same side when that weird twisty transition state unwraps. Whereas that then means that the R and the methyl are on the same side. You then get a slow elimination of the triphenyl phosphine oxide to give the double bond. So what can happen? What are the other alternatives? Well, if we put the R pointing towards the phenyl, well, we get steric clash. The lower energy transition state, which gives us the cis, puts the methyl as far away from the R group as it can, while the R group remains away from triphenylphosphines. Conversely, if you put the methyl on the same side as the R, well, you're going to get a trans double bond. Okay, so these alternative transition states suffer from a variety of different steric clash. It's just trying to find the lowest energy one that you can. Okay, and of course the driving force for this reaction is the P plus O minus. Same as we said with the sulfur. It's not best to think of that as a double bond if you can. So, an example in synthesis. Well, we can take 1, 2, 3, 4 pentyl bromide, and you react with triphenylphosphine in ether, and the salt precipitates out of solution. Nice. And Wittig salts have a pK of around 20 to 22, depending on your substituents. Stabilized Wittigs have a lot lower. You can then do a treat that with LDA. LDA has a pKa of around 37, so easy deprotonation, and then you react it with the ester aldehyde shown below the arrow to give this alkene, which I think is a pheromone, but I forget which one. Here is a more complex example, and we kind of like teased this slightly before, and this is from Noyori's synthesis of the prostaglandins. And we'll talk more about this during the stereochemistry part of this course, I think. I think this is Noyori. No, this isn't Noyori. My apologies. We will talk about this system again, but this is a total synthesis. It is definitely the prostaglandins, though. The prostaglandins are very important molecules that are involved in a lot of cellular signaling, and a classic biological response they're involved in is pain. But there are prostaglandins involved in childbirth and all sorts of stuff. So, remember we talked about Wittig reactions and hemiacetals earlier? Well, deprotonation favors ring opening. Like that. And, oh, my apologies. That then, upon ring opening, can do a Wittig reaction to get you through to the prostaglandin skeleton. Right. Now, stabilized ilids give trans products. No, not really. This is broadly an explanation that's given to undergrads to help explain this. And no. This is still, oh, what happened there? It's still a 2+2. but it's a later transition state. Okay, what that means is all this is horseshit, frankly. If we just go back a couple of slides, what we're saying in a late transition state is that in a early transition state, so an early transition state means that the transition state looks a lot like the starting materials. Okay, a late transition state means that the transition state looks a lot like the products. Okay, so in a late transition state, you need to consider interactions that are unfavorable in the product, whereas in an early transition state, you're looking at interactions that are unfavorable in the starting material. So in this unstabilized transition state that we have here, starting material interactions are important. Okay. In a late transition state, steric clash in product, more important. Okay, because it looks a lot closer to this in the transition state than it does to this. This is something that we can genuinely talk about for ages, and I don't want to because it goes into a lot of orbital detail that really we don't need to know. We've got a lot more to discuss. The only thing that I will say is that Horner-Wadsworth-Emmons reactions oh my goodness, that's just disgraceful. Sorry. W-A-D Worth. Are like enolates. Okay, so this is true when you're looking at phosphorus, double bond oxygen, ETO2. It is not the case for ilids. So okay, so please don't worry about it too much, but please be aware that yes, people are lying to you again. And I'm trying not to lie to you, I'm just going to gloss over things. Okay, so here's some examples of some Horner-Wadsworth-Emmons reactions. This is obviously a carbohydrate-like substrate. And this is quite a cool reaction because you get your alpha-beta unsaturated formed as an intermediate, but that then undergoes conjugate addition to give a a carbosugar type product. And now that I think about it, that could actually be really interesting for some of our stuff. Shall have to think about that more. Okay, so some examples from the literature. Great. So here's the Horner-Wadsworth-Emmons reaction, and like I said, the mechanism we were showing previously seems to work for that. And you make this reagent, the Horner-Wadsworth-Emmons reagent, through the Michaelis-Arbusov reaction, or sometimes just referred to as the Arbusov reaction. You take an alpha halo carbonyl compound, most often an alpha halo ester, and the phosphorus does a nucleophilic displacement of the bromide to generate a phosphonium, and the bromide can then actually react with that to give the phosphonate, okay, plus ethyl bromide. That works particularly well in non-polar solvents because you don't want to have this salt present in solution in a non-polar solvent. We're not going into the mechanism because it was really on the previous stage, but the key thing is that that reacts with an aldehyde as if it was an enolate. Yep. Okay, and then you get closure like we didn't talk about on the previous slide. The one to really watch out for, though, is this one here, because it's a stabilized anion, but with trifluoroethanol as your ester component, your phosphonate ester component. And that, in actual fact, gives cis-selective reactions. And that is sometimes known, or usually known, as the Stilganari modification. Okay. There are other modifications as well, but this works really quite nicely a lot of the time. And one of the great reasons to use Hornwoods with Emmons is because this product is neutral. You can deprotonate it with a base to generate an anion, and the anion is more reactive than standard Wittig ylide because it's actually anionic rather than neutral. Okay, it also gives a product which is shown here, and that is water soluble. Water soluble byproduct, and that's typically a lot easier to get rid of than the triphenylphosphine oxide that you get with a Wittig reaction. Triphenylphosphine oxide is often the bane of synthetic chemists because getting rid of it is such a pain in the bottom. Okay, here's the mechanism that we didn't talk about before. Enolate. The key thing is that this is slow, this is fast. Okay, this is the reaction for the Hornwoods with Emmons. This is how the HWE works, the HWE reaction. But not the Wittig. Okay. Yeah. Okay. That brings us to the end of that section. The next bit is the extended enolate problem, which is cool and interesting, but I think it would be a good time to take a 5-minute break. And yes, we will keep that. Okay,